conception that telescopes, you try to make smaller things bigger, and that's what telescopes do. But that essentially is not like what telescopes do. Telescopes actually works as a collecting object. So what happens is, like, imagine there's a bucket in a rainy day, and it's collecting all the water drops from the sky. So the water here is the light, and the bucket here is the telescope. So it collects light and trying to make so that way actually you can observe the fainter objects that you cannot see with your eye. So it's basically telescope is basically a light collecting object. The bigger the bucket is, of course, you can actually collect more light photons from the sky, which means you can go fainter, right? So that's kind of how the telescope works. There are, in fact, a lot of telescopes all over the world on the mountaintops of like very dry and clear, where you can access clear skies, such as like shown in these examples like Chile and Hawaii. There's like these observatories. So there are actually telescopes all over the world where probably it's not accessible by the public, but astronomers use them to do their science. But then why do we have to care about space telescopes? Like, there are telescopes already on the ground, but why are there space telescopes? Now, essentially there are two reasons. I'll try to simplify this. The first one is, if you go to space, you're no longer limited by the turbulence on the Earth's atmosphere, which means that you get sharper images than you see from the Earth. Because the atmosphere of the Earth, while it protects us from a lot of things from space, it actually also kind of makes all the images fuzzier. Because you see some stars blinking, that's because of the Earth's atmosphere and things like that. So that's the first reason. Second more important reason is light is not only confined to the visible wavelength, like the rainbow color, basically, from the violet color all the way to the red. It's not only confined to that. There's a very wide range of light, from gamma ray, X-ray, ultraviolet, and then visible light, infrared, and then radio. So if you go to space, you can actually access all of this. But if you're limited to Earth on the ground, you'll only get these small windows of a means to access that kind of whole wavelength. So that's why you need space telescopes. Okay, I'm going to start a story about the Hubble Space Telescope. So the Hubble Space Telescope has been, it's been launched back in 1990, so it's been actually orbiting around the Earth 15 times a day. It's still orbiting around the Earth as we speak, 15 times a day. It was launched 35 years ago. It's the mirror size about 2.4 meter in size. It's designed to observe the UV, optical, and the infrared bands. And there are some challenges that recently Hubble has been facing. So it was originally designed to only last like 15 years. But they actually, when there was space shuttle, it's no longer, space shuttle is no longer operating. By the way, when there was space shuttle, a space shuttle actually went up to Hubble Space Telescope 5 times to refurbish the instruments and replace the batteries and also the solar panels. So actually, the life was extended to until now. It's still doing a lot of good science. And the current orbit is at about 510 kilometers, and it's still decaying. It's going down because air is, although very thin, the air is still there. So like the Hubble Space Telescope has some drag, and it's slowly coming down. So maybe like in 5 years, we'll eventually have to make it drop to the ocean, or maybe there's going to be a mission to actually boost the orbit to higher orbit so we can use it later on. But nothing has been decided yet. Now, despite that challenge, Hubble has been actually making a lot of good discoveries and a lot of good science. Now this just showed an example in the 35 years what kind of beautiful images Hubble has produced. Each image is actually an anniversary image celebrating each year of operation. And not just to our eyes, they're beautiful, but they have been making a lot of good revolutionary scientific progresses. So that's what Hubble has been doing. Now, perhaps one of the most iconic discovery or the science results of Hubble was based on an innovative but kind of risky idea to stare at a seemingly blank patch of sky for 100 hours. So there were some astronomers who kind of like thought in an innovative way that, hey, let's try something like that other people haven't done. So what they did was they stared at this like small piece of patch on the sky to place Hubble and observe for 100 hours. Now, how small is this patch of sky? Like, imagine you go to a beach and then you pick up a grain of sand and then you stretch your arms and you try to cover that with the sky. And that's how small it is in the arm length. It's that small patch of sky, and Hubble was peered through this patch of sky for 100 hours. What astronomers found was astonishing. Thousands of galaxies in just that, what they thought to be a blank patch of sky. There were thousands of galaxies that actually was discovered, as is in this picture. This was called the Hubble Deep Field. Back then, it's still called the Hubble Deep Field. And this image basically changed the way astronomers actually study the universe forever. So it's kind of the beginning, it marked the beginning of modern observational cosmology. And people thought about, hey, how do we actually study the early universe and study all these galaxies better than Hubble? So in a way, Hubble, this result also gave some ideas about how to design the next generation telescope, now known as the James Webb Space Telescope. It gave the design philosophy. So the first requirement for the James Webb Space Telescope was pretty simple. If you want to look at more fainter objects, just as I kind of introduced you in the first slide, one of the first slides, you need to make the mirror bigger, right? You need to make the bucket bigger so you can collect more rain at a given time. So just make the mirror size bigger, as big as you can, but still you need to actually make it fit into the top of the launch vehicle, the rocket, right? So that's why they designed it such that it's a foldable mirror like this, and then you can fit inside the top of the rocket like that. The second requirement was such that Webb has to be, I'll call it James Webb Space Telescope, like I'll abbreviate it as Webb from now on. So Webb has to be extremely sensitive to infrared light. Now this is because something called a redshift effect. So we know that, I think a lot of you heard about the fact that the universe is expanding, right? So light is kind of a wavelength. This is the hardest part of this talk, so like stay focused, like before falling asleep. I know. So light is kind of a wave and a particle at the same time. And the wave part of light actually makes things get stretched as the universe expands. So a good analogy is this. I hope I have kind of a rope here. Maybe I can use this. Like, imagine like someone's kind of making a wave like this, you know, like with a rope, okay? And then the observer is there. Now you kind of run away with the rope. Then what happens? Like doing this, the wavelength gets like longer, right? It gets longer. If you run toward that person, the wave gets like shorter. It gets like more higher frequency. So that's what's happening. Like the universe is kind of like receding away from the observer. So what we observe is that the farther away an object is, the farther away a galaxy is, the wavelength gets longer, which means that it gets redder. Because longer wavelength means redder. So that's why it's called the redshift. So that's what's happening in this like figure here. So, and that is why Hubble was only meant to observe ultraviolet visible and a little bit of infrared, while James Webb, you can see that it's observing a lot more into the infrared. So that's how it was designed. Now, being sensitive to the infrared meant that, So being sensitive to infrared meant that you have to send the telescope away from Earth at a distance of 1.4 million, 1.5 million kilometers at the second Lagrange point right there. So right now, and because of that, STScI had to actually deploy a lot of systems while folded up. It had to deploy a lot of systems, and this movie basically shows that. And now, James Webb is kind of orbiting around the sun at the same period as the Earth, like this. You may notice that JWST is also facing away, the mirror and the cameras are always facing away the sun to keep it cool, and it's always shadowed by the sun shield. Okay, I gotta probably speed up some things here, but once we arrived at the L2 point, the mirror alignment process began, because there are 18 different mirror segments and they're all misaligned, and for 3 months we actually had to spend our efforts to make such that the 18 mirror segments act as a single large 6.5 meter mirror like this. So this kind of shows the process we went through for the 3 months. And once this was over, on April 22nd, 2022, we celebrate the completion of our mirror alignment by eating a cake, of course. What else do we do, right? So now I'm going to take you to a journey, basically, I'll just shorten it. I'll show you a pretty picture taken by JWST, okay? From now on. It's a journey to distance and time, and I'll just showcase some examples of, starting from the solar system here, we have Jupiter, Saturn, Uranus, Neptune. And because in infrared light, you're kind of detecting lower temperatures, what happens is the rings actually get more prominent than the pictures you used to see. So rings are made of ice particles, which means that they have very low temperatures. Infrared is good at seeing those ice particles. That's why you see them more prominent. It also can infrared can also pierce through the atmosphere in some cases. That's why Neptune kind of seems like a glass marble, Yuri-Gusar, right? That's why I always kind of think about this. Right, let's go to a little bit further distance out to a few thousand light years. The famous Carina Nebula. This was one of the images that was announced in July 2022 when we said James Webb is ready to actually take the science. And I'm sure some of you actually put this as a computer background, at least at some point. What's happening here is Carina Nebula is a stellar nursery where stars are being born. And the stars are being born down here as well as up here. And the stars already born up here are radiating a lot of ultraviolet energy. That's why it's kind of carving out all these stardust. So you're actually left with a two distinct color, blue and orange down here. That's why it's also nicknamed the cosmic cliff. And another good example of a stellar nursery where stars are being born, this is called the pillars of creation for a good reason. And here I'm showing on the left an HST version of that. On the right is the James Webb Space Telescope Near Eye Refrigeration. You see the difference, in the HST image, most of the stars are kind of hidden by the dust in front of in the foreground, while in the near infrared, you see a lot of these stars actually start to get visible because near infrared is good at piercing through all these dust, right? But if you go to even longer wavelength, looks kind of spooky, right? This was actually released as part of the Halloween image because of this color. But now, if you go to the mid-IR, even further out to the IR, now you're getting more sensitive to the very low temperature dust. So you see a lot of the details of the dust kind of forming this nebula. But instead, the stars starlight kind of become subdued now because it's too far out in the mid-IR. Because stars are hot, right? But dust temperature is low. That's why you see this kind of thing. Okay, this is my favorite picture, a protostar. Protostar means a just-born star. And this is actually a simulation image on the left where it shows that the gas cloud actually gets compressed, and then the energetic star actually starts to emitted energy through the polar north and south pole and creating these jets. So this star, it's not a star yet, by the way. Protostars are not hot enough to actually start the nuclear fission yet. So that's why it's hidden inside a very small dust band here. But it's just, like it's just like an art piece. It's just like creates these energetic jets, like to the either side of the nebula, and that's what's happening here. Now, stars are not only beautiful when they are born, but also when they die off. Like this is an example of what's called a planetary nebulae. And a sun-like star, our sun, might go through one of these phases. It's called planetary nebula because when you look at them through the telescope, they look like planets, but they're actually not planets because it's its name from there. But what's happening is the stars are dying off, and then they're like ejecting materials outside now because they have less energy to actually heat all the materials. So, but the reason they look different is because sometimes there are stars that actually orbit around another star, and that's what makes all these differences. Their orbit may be different, the star may have different masses. So there's a lot of variety on how these look. This one was released like recently, and it's called the Cranium Nebula for those who are doing biology. It looks like inside of the brain. That's why it got its obvious name. More massive stars, like maybe like 10 times more massive than the sun or more, they go through a very violent phase instead of like a quiet like planetary nebula phase. So, and that's what's called the Wolf-Rayet stars. And these kind of show the examples. Again, sometimes stars are orbiting around the other star and making these kind of like spiral shapes. In this case, like kind of light echoes like this. But anyway, what happens is once they end their lifetime in these Wolf-Rayet phases, they explode as supernovae. You probably heard of supernovae. And what's left is called the supernova remnants. And this is a good example of that. I call this image a space dragon. Is it obvious? Okay. So Cassiopeia A, it was a remnant of a supernova that exploded about in year 1680. And the left one is again near IR, right one is a mid-infrared. So like two different versions, and this kind of emphasizes why it's important to actually look at the same object using different wavelengths and different telescopes, because you get to study different characteristics of like the celestial objects. Okay, now I'm going to show you some galaxies here. The galaxies are a bunch of stars living together. This one on the left here is like the left side is the HST image, on the right is a JWST. The middle one is showing an interaction of galaxies, but this one was kind of nicknamed a penguin and its egg, a penguin galaxy basically. On the right is Stephan's quintet, where like now more than 3 galaxies are like kind of colliding together to make this kind of a beautiful shape. This is at the distance of several hundred million light years. We're now like going really far, and if you go even farther out, there's this image. This was also released as part of the first images of a JWST, but this is a cluster of galaxies called SMAX 0723. It's at a distance of 4 billion light years now. We're going really back in space, very far away. And the cluster of galaxies itself is kind of the fuzzy object that look like in a color of white and yellow here. But you might also notice these like distorted kind of shapes too. I marked them in red here. This is because of what's called a gravitational lensing. So what's happening here is the massive galaxy in the middle, the SMAX 0723 galaxies, are acting as cosmic magnifying glasses that actually bends to space-time, and also bends the lights that coming from the background galaxies, which are located at a distance more than 10 billion light years ago. So by the time they arrive at us, what happens is some of the galaxies, the same galaxies, are seen like 3 times, some of them 2 times. But anyway, these cluster of galaxies act as a magnifying glass. And this was predicted by Albert Einstein, about century ago, and now JWST is using that phenomenon as its own telescope to peer through the deep sky and study the objects that are in the early universe. There's another telescope coming up that's called the Roman Space Telescope, which will, instead of going through a small space, it's going to actually observe a very wide area. Although it's not going to go as deep as JWST, now we're actually going for a wider, shallower approach. So this Roman Space Telescope was supposed to launch next year in May 2027, but this is probably the first project that NASA has been pursuing that's actually going to be launched before the expected date. So it's right now the launch date is around like September to October this year. So I'm going to be pretty busy in the next few months because of this. The key science topics it's going to actually study is like dark energy, dark matter, and some exoplanets. So now, so far I actually talked about how we got here using the JWST, like pictures and everything, but that's only half of the story. The other half is, are we alone? And to answer that question, we need to go look out and find exoplanets. Exoplanets means planets orbiting around another star, and they come in very wide variety. Here they're categorized as like 5 different ones. The first one in the middle is habitable zone planets, just like our Earth. Okay, the other ones are like this, called like hot Jupiter, super Earth. Super Earth is a bigger Earth, so it has more gravity. So it has like less chance of harboring life. So JWST and HST has already kind of had some breakthrough about measuring some of the atmospheres of these exoplanets, like as shown in this example. The idea is to analyze the light going through the starlight going through a planet atmosphere to get the fingerprints of like what kind of elements are in those atmospheres. And in this case, this is a hot Jupiter, so there's no chance there's any kind of life form is gonna live here. But the important thing is that this JWST has proven that this kind of technique works. Now, if we're essentially interested in life, if there's going to be life in other planets, right? And that's where the Habitable World Observatory, which is going to be launched 15 to 20 years from now, is going to do. So essentially what it's going to do is it's going to try to find a Earth 2.0. So that's kind of the basic concept of this Habitable World Observatory. It's going to have a mirror the size of 6 to 8 meters, so probably a little bit larger than a JWST. Still far away. So I'm gonna. So going back to these two big questions: how did we get here? It's getting answered by the Hubble Webb enrollment. Are we alone? It's started to get answered by JWST and maybe Roman, and then in the future by the HWO. So it was kind of the journey I wanted to bring you about, and this was the last slide. So I'll stop here and then I'll take some questions. Thank you.
Silence starts to sound. You catch gold